This is Edexcel A-level Mathematics, paper 3. Now you notice on the front here it says paper 3-1 statistics. That's because they've split it up into, a statistics and a mechanics paper, but you would be sitting all of this in the same session. So in this video I'm going through statistics and mechanics, and this is from the 2019 A-level exams. Please have a go at this paper before watching this video. You'll need the mathematical formula and statistical tables and a calculator. Let's get into it. Question 1 says 3 bags A, B, and C each contain 1 red marble and some green marbles. Bag A contains 1 red marble and 9 green marbles only. Bag B contains 1 red marble and 4 green marbles only. Bag C contains 1 red marble and 2 green marbles only. Sasha selects at random 1 marble from bag A. If he selects a red marble, he stops selecting. If the marble is green, he continues by selecting at random 1 marble from bag B. If he selects a red marble, he stops selecting. If the marble is green, he continues by selecting at random 1 marble from bag C. Part A says draw a tree diagram to represent this information. Okay, so we're going to have 3 picks on this tree diagram. So let's give ourselves enough room for 3 picks. The first one, we can either get red or green. And if it was green, then we went ahead and picked another one. If it was red, the tree stops. So from green, there's going to be another branch on this tree. And again, if it was green, we went on and made a pick from bag C. So we're going to have another branch from the green section or the green branch. And again, it could be red or green. Okay, so they're my branches. And this was the first pick from bag A. This was the second pick from bag B, and this was the third pick from bag C. Okay, so we also need the probabilities. So for bag A, we had 10 marbles. One of those was red, so we'd have a 1 out of 10 chance of getting the red marble on the first pick, and then a 9 out of 10 for the green marble on the second pick. On the second pick, we had 5 marbles in bag B, and so therefore 1 out of 5 for red and 4 out of 5 for green. And then in bag C, the third pick, we had 3 marbles. One of those was red, so the probabilities there would be 1 out of 3 and 2 out of 3 for green. Okay, so that should be everything we need for our tree diagram. And part B says find the probability that Sasha selects 3 green marbles. So for this question, we're looking at this branch here. So we're going from green, and then we picked another green, and then we picked another green. So when you're using a tree diagram and you go along one branch like that, you multiply the probabilities. So for this one, we're going to do 9 out of 10 multiplied by 4 out of 5 multiplied by 2 out of 3. And that should give us our probability. Well, how could we evaluate this? We could just put it straight into a calculator. Yeah, let's just do that. Actually, let's get, so 9 times 4 is 36 times 2 is 72. And then 50 times 3, 150. And then let's put that into a calculator. How about that? So 72 on 150 gives me 4.48 or 48%. However you want to write that would be fine. Okay, so that was part B. 48% chance of selecting 3 green marbles. Part C says find the probability that Sasha selects at least 1 marble of each color. For these types of probability questions, that can help to rephrase the question to yourself. So what does this mean if we had at least 1 marble of each color? Well, it means that we're not getting all green or just red. We're getting 1 of each. So in other words, we're getting every possibility except green, 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 or this first red. Okay, because if we picked red on the first try, the probability tree ends there, and we don't make any more picks. So we want every possibility except green, 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 and red. So that means it's going to be 1 take those probabilities. So what I want to find first for part C is to find the probability of green, 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 which I actually did in part A, right? That was the probability of 3 greens, or the probability of just that first red. So this is going to be this probability here, 48%, 0.48, plus the probability of that first red, which was 1 out of 10, or 0.1. Okay, so this is 0.1. This equals 0.58. So that's the probability of just getting one color. I'm looking for the probability of at least one red one red and green. So everything else, this is going to be one take, 0.58. This is going to be 0.42. Okay, so that's the final answer for part C. So it can often help to kind of reverse the problem like that and switch it around, and that can make the problem a bit easier sometimes. For part D, it says, given that Sasha selects a red marble, find the probability that he selects it from bag B. There are a couple ways to do this problem and think about this problem. I'm going to use conditional probability because this is a conditional probability, right? The condition is he selects a red marble, and we want to know the probability that it is from bag B, from the second pick. So that's how I'm going to approach this for part D. So firstly, well, let's write down the conditional probability formula. We're looking for the probability that the red is from bag B, given that it's red. And the formula says this will be equal to the probability of picking the red token or marble, intersect the probability of a red divided by the probability of a red marble. Now we can interpret this numerator a little bit, because if it's red, right, the intersection here is going to be equal to the probability of a red marble. So let me just write this out and try to explain it a little bit. This is equal to the probability of the red marble from bag B, because this is red already, right? So if you're thinking about this in terms of a Venn diagram, well, we'd have the set of red marbles, and then inside that we have the set of red marbles in bag B. So that intersection is just this set here. Okay, so that's my way of explaining this, the fact that the intersection of those two things is just equal to the probability of the red marble from bag B. So therefore this probability of a red marble, given that the marble is red, is just the probability of the red marble from bag B divided by the probability of red marbles, of picking a red marble. Okay, so for this formula, we want to work out, or for this probability, we want to work out the probability of getting a red marble, and then the probability of getting the red marble from bag B, and then divide them. So the probability of a red marble is going to be all of these branches added together. So if I just rub this out quickly, I'm going to highlight the branches we're looking at. We're looking at this branch plus this branch here plus this branch here. So we're going to multiply these probabilities and then add them up, and that will give us the probability of picking a red marble. So we've got, for the first branch, it was 1 out of 10. Oops, still have the highlighter. It was 1 out of 10 plus 9 over 10 times 1 over 5. 9 over 10 times 1 over 5 plus the last red marble was 9 over 10 plus 4 over 5 plus, multiplied by 1/3. Okay. And that's going to give us the probability of red marble. Let's go ahead and evaluate this. It might be easier doing this as decimals, probably, but there you go. I'm used to using fractions. This is 36 over 150. And let's just go ahead and use a calculator for that and get our decimal answer. So 0.1 plus 9 over 50 plus 36 over 150. And I get 0.52 for the probability of a red marble. And then I want the probability that the red marble is from bag B, the second one. That's going to be 9 over 10 That's going to be this red branch here, 9 over 10 times 1/5. That is 9 over 50 equals 9 over 50. Okay, and then as I said, the probability of the red marble from bag B being selected, given that the marble is red, is these two things divided. So let's actually get a decimal answer for that. 9 over 50 is 0.18. 0.18, so this is going to be 0.18 divided by 0.52. And for a final answer then, I get 0.18 divided by 0.52, 0.346, and so on. 0.346. And did it say to round off? No, so we're going to round that off to 3 significant figures. As it says on the front page, this will be 34.6%. Okay, that was part D for question 1 for a total of 8 marks. After I finished this problem, I realized there's another way of finding this probability of a red marble. If you look at the tree diagram again, if you've got a red marble, there's only one other event that is not happening. So you're not getting 3 greens. You're getting a red or a green and a red or a green and a green and a red. So you can do one take the probability of getting 3 green marbles, and that will also give you the probability of a red marble. So for this number here, 0.52, we could also have just done the calculation. Probability of a red marble equals 1 take the probability of 3 green marbles. And I'm not sure why I didn't see that, but this would just be, well, take our answer from here, which we worked out in C, or sorry, we worked out in B. We would do 1 take 0.48, which is 0.52. Anyways, it's always good to see different ways of calculating the same thing. So just a quick note to add in before we go on to question 2. Question 2 says the partially completed box plot in figure 1 shows the distribution of daily mean air temperatures using the data from the large data set for Beijing in 2015. An outlier is defined as a value more than 1.5 times the IQR below Q1 or more than 1.5 times the IQR above Q3. The 3 lowest air temperatures in the dataset are 7.6, 8.1, and 9.1. The highest air temperature in the dataset is 32.5. Complete the box plot in figure 1 showing clearly any outliers. Firstly, I want to find these values, 1.5 times the interquartile range, and then what is that below Q1 and above Q3 to see if any of these are outliers, and then I'll be able to draw my whiskers in as well. So firstly, let's find the interquartile range. Firstly, we need the lower quartile and upper quartile. They are the ends of the box here. Looking at the scale on this axis here, we're going up by 0.2. So this line here is going to be at 19.4. And then this one up here is going to be at 26.6. Let's do some calculations down below to find my boundaries of the upper and lower outliers. Firstly, let's write down the quartiles. So the lower quartile was 19.4. The upper quartile was 26.6, and then the interquartile range is the difference. So 26.6 take 19.4. I'm going to use a calculator for that. 26.6 take 19.4, and I get 7.2. And then I want to do 1.5 times 7.2. Again, with the calculator, 1.5 times 7.2, I get 10.8. Okay, so the lower quartile, take 10.8. Let's see what that is. 19.4 take 10.8. I get 8.6. Okay, and then 26.6 plus this range or this value, 10.8. 26.6 plus 10.8, and I get 37.4. Okay, so looking at those values again, my lower boundary is 8.6, and I have 2 temperatures below that. So 7.6 and 8.1 are going to be outliers. My upper boundary was 37.4, so that's not going to be an outlier. So that means then that we could draw our whiskers in. Now for your minimum and maximum, you can either choose these values or the boundaries. So I'm going to choose 9.1 as my minimum because that's the minimum in the data set. So that's going to be here between the grid lines. Okay, so that's 9.1, that's my minimum. And then my max is 32.5. Should be about here. Okay, so that's my maximum. So they're my whiskers. And then my outliers, 7.6 is here, and 8.1 is about here. Okay, so these are outliers. Okay, so that was part A. Part B says, using your knowledge of the large data set, suggest from which month the two outliers are likely to have come. So for this, you need to know which months the large data set covers in 2015, and that is from May to October. And then you also need to think of your geography, so where in the world is Beijing, that's in the northern hemisphere. And then you know these months are from spring through to autumn. So which month is then most likely to contain the lower temperatures? That's going to be October in autumn. So my answer there is going to be October, as Beijing is in the northern hemisphere and that is in autumn. So October, as it is autumn in the northern hemisphere. Okay. So a few things you actually had to know for that question, but just the one mark there. Part C says, using the data from the large dataset, Simon produced the following summary statistics for the daily mean air temperature X degrees centigrade for Beijing in 2015. N equals 184. The sum of the X values is 4,153.6 and the sum of the squares is 4,952.906. Show that to three significant figures the standard deviation is 5.19. For this, you need to know the formula for the standard deviation in relation to the sum of the squares, and this is in your formula booklet, so you don't have to memorize this. For part C, let's write down N, that was 184, and the sum of the squares was 4,952.906, and then the standard deviation is equal to the square root of the sum of the squares divided by N. And then we just need to plug those in. So let's put them straight into a calculator. The square root of 4952.906 divided by 184, and I get 5.188, and that was meant to be to three significant figures, so that would be 5.19. 5.19 rounded off to three significant figures. Okay, so that was, oh, that's degrees centigrade as well. Okay, so that was part C. Part D says Simon decides to model the air temperatures with the random variable T, approximated by a normal distribution with mean of 22.6 and standard deviation 5.19. Using Simon's model, calculate the 10th to 90th interpercentile range. To work this out, we can find the temperature at the 90th percentile and the temperature at the 10th percentile, and then work out the range between those temperatures. But let's get started on D down below. So for D, we are told the temperatures can be modeled by a normal distribution with mean 22.6 and standard deviation 5.19, and we want the range of temperatures between the 10th and 90th percentiles. So for this, to work out the temperature at the 90th percentile, we can use our calculators. Now you can do this using z-scores and working it out kind of manually, but why not use our calculators, save our brain power for gaming and other important things. We can use the invnorm function in our calculator, and we need to put in the percentile. So I'm looking for the 90th percentile here, and then put in the mean and the standard deviation, and I get 29.25. So that's saying the temperature at the 90th percentile is approximately 29 degrees. So I'm just going to write out what I put in and then my result. So rounding this off is 22.25. Actually, I don't even need to write that down. What I can do is say this whole thing will equal this value, take the temperature at the 10th percentile. So then let's take that answer and subtract the temperature at the 10th percentile. So 0.1, 22.6, and 5.19. And that will give me the range of 13.3. So writing down what I entered, this was the 10th percentile. And make sure that you are understanding how to do this manually as well. That would be my suggestion. So we had to round that off to 3 significant figures. That was 13.3 degrees. For that range, for question D, part E says Simon wants to model another variable from the large data set for Beijing using a normal distribution. State 2 variables from the large data set for Beijing that are not suitable to be modeled by a normal distribution. Give a reason for each answer. Typically, data that cannot be modeled by a normal distribution is qualitative data or categorical data. You know, things like eye color. You cannot model eye color on a normal distribution because you've just got brown, blue, green. That doesn't make sense. You need numerical data or quantitative data. Here you need to try to remember what sorts of data is modeled in the data set, and hopefully you can remember that wind speed is one, specifically wind speed on the Beaufort scale. So the Beaufort scale gives things like calm, light air, light breeze, gentle breeze, all the way up to violent storm and hurricane. That is qualitative data or categorical data, which cannot be modeled by a normal distribution. And the other one is harder because you actually have to remember what the data looks like from Beijing in 2015. You need to have probably worked with the data and seen that the rainfall data cannot be modeled by a normal distribution, because basically all of the values for rainfall from that period are zeros or ones. So there was very little rain in Beijing in this period. Now you could, I guess, think of that logically and say, well, if Beijing is in summer, spring and summer, then it's going to get little rain, but I think that would be tough to think of that unless you've actually seen the data. So there are the two answers here for part E. We have wind speed on the Beaufort scale, and I'll just go ahead and write these out. And this was because it was qualitative or categorical, and the other one was rainfall because it is not symmetric. It would not fit a normal distribution because basically there are just too many days with zeros, so lots of days with zero rainfall. Okay, that was part E, and that really shows how much you need to have worked with the large data set to get that one correct. Okay, so that was question 2 for a total of 11 marks. Question 3 says Barbara is investigating the relationship between average income, GDP per capita, ex US dollars, and average annual carbon dioxide emissions, Y tons, for different countries. She takes a random sample of 24 countries and finds the product moment correlation coefficient between average annual CO2 emissions and average income to be 0.446. Part A says stating your hypothesis clearly, test at the 5% level of significance whether or not the product moment correlation coefficient for all countries is greater than 0. Let's set up our hypothesis test then. So we have an R of 0.446, a sample R, and our hypothesis will be, our null hypothesis will be that rho, the population coefficient, is 0. Our alternate hypothesis is rho is greater than 0, or there's a positive correlation, and we're testing at the 5% significance level, so alpha is 0.05, and we want to find a critical value, and we're going to do that using our tables from our formula booklet. So let's bring that up. This is our formula booklet, and if we go down to our correlation coefficient table, critical values of correlation coefficients, that is on page 37. There were 24 countries in this test, and we were testing at a 5% level of significance, so our critical value there is 0.3438. 0.3438. So that is clearly less than our sample R. So this would suggest then that our R in this sample is significant. And this suggests there is a positive correlation. So let's try to summarize this. This suggests So this suggests the correlation coefficient for all countries is greater than 0 at the 5% significance, so we should accept the alternate hypothesis that rho is greater than 0. This suggests positive correlation. So that was part A. Part B says Barbara believes that a non-linear model would be a better fit to the data. She codes the data using the coding m equals log x and c equals log y and obtains the model c equals negative 1.82 plus 0.89 m. The product moment correlation coefficient between c and m is found to be 0.882. Explain how this value supports Barbara's belief. Well, if she's saying that a newer model would be a better fit and the correlation coefficient between the two variables is now higher, 0.882, meaning that it is a stronger correlation, it's a stronger positive correlation, closer to 1 being a perfect correlation, then it clearly supports her belief because we're getting a closer correlation between the variables with the new model. So let's try to summarize that for part B. So I would say this is a stronger correlation. So this is a stronger positive correlation than in part A, as 0.882 is closer to 1, therefore the new model is likely to fit the data better. Okay, so that was part B, and part C says show that the relationship between y and x can be written in the form y equals ax to the power n, where a and n are constants to be found. For this question, you need to use this equation here, c equals negative 1.82 plus 0.89 m, and then write it in this form y equals ax to the power n. So I might do part C down here. We start with c equals negative 1.82 plus 0.89 m, and we also said in the question that m equals log x and c equals log y, so plugging those in, we have log y equals negative 1.82 plus 0.89 log x, and now I want everything in terms of log base 10 to get rid of the logs. So I already have log base 10 of y. This becomes an issue. Negative 1.82, I want to write that in terms of log base 10. So what would 1.82 equal if I introduced a log there? Well, it would be log base 10 of 10 to the power 1.82. That would equal 1.82. Well, if this was a negative, it would be a negative power. I can write this then as log base 10 of 10 to the power of negative 1.82 plus, and also I want to take this coefficient and raise it to the power of x here. So I have log base 10 of x to the power of 0.89. Then also I can combine these logs here using the fact that log of a plus the log of b equals the log of a times b. I can write that as log of 10 to the power of negative 1.82 multiplied by x to the power of 0.89. And then raising everything to the power of 10, I'll have y equal to 10 to the power of negative 1.82 times x to the power of 0.89. And then I almost have it in this form, y equals ax to the power n. I just need to find the value of this. So 10 to the power of negative 1.82. Let's get that as a decimal. And I get 0.015 and so on. Now, sorry, just checking the question again. It doesn't say at what accuracy to give a. It just says it's a constant, so we could round that off to 3 significant figures. So this would be 0.151. So we could write this then as y equal to 0.0151 multiplied by x to the power of 0.89, and therefore a is equal to 0.0151 and n is equal to 0.89. So that would be my final answer there for part C. Again, a equal to 0.0151 and n equal to 0.89. And that was question 3 for a total of 9 marks. Question 4. Magali is studying the mean total cloud cover in octaves for Laucars.
Luchas. Luchas.
In 1987, using data from the large dataset, the daily mean total cloud cover for all 184 days from the large dataset is summarized in the table below. One of the 184 days is selected at random. Find the probability that it has a daily mean total cloud cover of 6 or greater. Okay, so 184 days, we are looking for the probability that it has 6 or greater, so that's these ones here. Actually, let me use a highlighter there. We're looking for the probability that it falls into this category here. So let's add those up. Divide by 184, that should give us our probability. So 52 plus 52 plus 28, that's going to be 132 divided by 184. That should be our probability. So probability that the octets is 6 or greater. That looks like an O actually. So octets is 6 or greater. This is equal to 132 on 184. And this is equal to something 184.717. Or, well, let's write that down, 0.717, which we could write as 71.7%. Okay, that was approximately, so I should use approximation signs there. Part B says Magali is investigating whether the daily mean total cloud cover can be modeled using a binomial distribution. She uses the random variable x to denote the daily mean total cloud cover and believes that x is approximated by a binomial distribution with a sample size of 8 and probability of success of 0.76. Using Magali's model, find p of x greater than or equal to 6. Okay, so this is going to we're going to be able to compare this to part A and see how accurate this model is. So for part B, part 1, we can use the binomial cumulative distribution function. So this would be 1 take the probability of x less than or equal to 5, because that's how I need to put it into a calculator. So this would be 1 take the binomial CDF of sample size 8, probability of success 0.76, and maximum of 5. Plugging that in, that will give us the probability that's greater than 6. So using the distribution function on my calculator, I have 8, 8.76, and 5 as my statistics. I get 0.703 rounded off, 0.703 to 3 significant figures. So 70.3% for this variable. In this case, we're talking about cloud cover greater than 6, and that is similar to my answer in part A. And part B, part 2 says find to one decimal place the expected number of days in a sample of 184 days with a daily mean total cloud cover of 7. For this, I'm going to use the probability density function. So this gives you effectively a point probability on the binomial distribution. And that is in the distribution menu as well. So go down to probability density function and input, well, I'm looking for the probability that x equals 7. And I'm going to put in 8.76 and 7. So plugging those in, I get 0.281 to 3 significant figures, 0.281. Now let me just check that I've answered the question. It said the expected number of days. Okay, so I've got the probability. I now need to multiply that by 184 to get the number of days. So 0.281 0.281 times 184. Let's do that. Times 184. That gives me 51.7 or 51.723 significant figures. Okay, so that's approximately 51.7 days with a cloud cover of 7. So comparing that to the data, that's pretty good as well, pretty close for a binomial distribution model. Okay, so for C says explain whether or not your answers to part B support the use of Magali's model. Yes, it does, as I've said. Part B, part 1 was close to my answer in part A, 71.7% and 70.3%, and 51.7 is close to 52. So to answer that question, yes, they do. So 0.703 is approximately 0.717, and 51.7 is approximately 52. So these answers do support Magali's model as they are close to the actual historical data. Okay, that was part C. Part D says there were 28 days that had a daily mean total cloud cover of 8. For these 28 days, the daily mean total cloud cover for the following day is shown in the table below. Find the proportion of these days when the daily mean total cloud cover when the daily mean total cloud cover was 6 or greater. So these are days after a previously very cloudy day with an octa of 8. This is kind of a conditional probability, if you like. So the probability that these were 6 or greater, 9 plus 9 plus 5, that's 23 out of the total of 28. Let's find that as a decimal. So 23 on 28. What is that as a decimal? 0.281 to 3 significant figures. Okay, so 82% has gone up, you can see, because, well, I guess if you have a really cloudy day, the next day is more likely to be cloudy. I guess that makes sense. Part E says comment on Magali's model in light of your answer to part D. For this, you need to know that binomial models measure independent events. To use a binomial distribution, you need independence. And this is kind of showing that cloud cover from day to day is not independent, right? If you have a really cloudy day or a really rainy day, it affects the weather the next day. You're more likely to have a cloudy day the day after that. So independence does not hold, therefore it's the binomial distribution is not appropriate here for this particular situation. So let's try to summarize that in an answer. And the first thing I'm going to start with is, in this case, we have a probability of 6 or greater of 82%. And the answer we got in part B, part 1, that would be the same every day using Magali's model with the binomial distribution. We'd always get 70.3%. So we can say then that 0.821 is greater than 0.703, and this indicates that independence does not hold. So I'll have a go at summarizing that. So I've said a binomial distribution measures independent events. From this result, the probability of octas greater than or equal to 6 increases after a cloudy day with octa equal to 8. This suggests the events are not independent, and therefore a binomial distribution is not appropriate. Independence does not hold. Okay, that was my answer to part E, and that was question 4 for a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 marks. Question 5 says a machine puts liquid into bottles of perfume. The amount of liquid put into each bottle, D milliliters, follows a normal distribution with mean 25 milliliters. Given that 15% of bottles contain less than 24.63 milliliters, part A says find to do decimal places the value of K such that P of 24.63, D between 24.63 and K equals 0.45. Okay, so we're looking for this probability of the amount of liquid put into each bottle, and we want K such that this range here is equivalent to 0.45 for this probability. To do this, we'll need some statistics about this normal distribution. Well, they give us the mean, and they give us the fact that 15% of bottles contain less than 24.63 milliliters. They don't give us the standard deviation. So we're going to have to find that first, and then we can find that constant K. So let's write down what they tell us. The mean is 25 milliliters, and the probability of the liquid less than 24.63 milliliters is equal to 15%. Firstly, let's find a z-score for that 15%. This will be, well, use the inv-norm function on your calculator or look up the tables. 0.15, I get 1.036 or negative 1.036 for a z-score. And then I can use that to find the standard deviation. So the z-score formula says that we have the x value, take the mean divided by the standard deviation is equal to the z-score. So I'll have negative 1.036 equal to 24.63, take the mean, which was 25, divided by the standard deviation. Solving this for the standard deviation, I would find that difference, divide by 1.036, 24.63, take 25, divided by negative 1.036, and I get 0.3571 for the standard deviation. 0.3571 milliliters. And now let me do a little bit of a diagram here to give a picture of what's going on. We have a mean at 25, we have a value at 24.63, and everything below that is 15% of this distribution. This is 15%, and we have some constant up here, K, such that in between these two is 45%. So what would that be up here then? Well, we'd have 45 plus 15 is 60%. So this bit up here would be 40% in here above K. So again, I could use the z-score formula to solve for K. So I could say that the probability of x greater than K is equal to 0.4, as I just showed here. And the z-score of 0.4 I can find again. So inv norm of 0.4, 0.4 is, I should do 0.6, sorry, so it's not a negative. Well, it's still going to be the same number. Anyways, I get 0.2533, so 0.2533, and now I'm solving for K, so I'm going to say that 0.2533 is equal to, I'm using this formula again by the way, but this time x is my unknown. This is equal to K, take the mean 25 divided by the standard deviation of 0.3571. Rearranging this for K now, multiply these together, add 25, and well, let's see what we get. This is multiplied by 0.3571 plus 25, I get 25.09 to 2 decimal places. So K is 25.09 milliliters. And going back to the questions to make sure I answered it, find to do decimal places the value of K. Okay, so done that, 25.09. Final answer for part A. Part B says a random sample of 200 bottles is taken. Using a normal approximation, find the probability that fewer than half of these bottles contain between 24.63 and K milliliters. Alright, what does this mean when they say use a normal approximation? Isn't this already a normal distribution? Well, not really, because when they're saying find the probability that fewer than half of these contain this amount of perfume or liquid, this is then a binomial distribution because we have a probability of success and we have a probability of failure. In other words, we have two outcomes. It can either be between those or not between those. So that's a binomial distribution, but we're going to use a normal approximation to find that probability. So for part B then, firstly, let's state that, well, we have a sample size of 200 and we have a probability of success, P equal to 0.45. Remember the probability that the amount of liquid between those two values was 0.45. They give us that in part A. And then we want to say that this variable y is approximately a binomial distribution with sample size 200 and probability of success 0.45. And then let's say this binomial distribution is approximated by a normal distribution, and we actually need to find that mean and standard deviation. So the mean for the approximation is going to be 200 times 0.45. That's how you find the mean of a normal approximation. 200 times 0.45, I get 90. And the standard deviation is the square root of n times p times q. Q is the probability of failure. N 200 times 0.45 times 0.55. Plugging that in, let's see what we get. 200 times 0.45 times 0.55. I get a 7.036 rounded off, approximately 7.036. Okay, so this is a normal approximation with mean of 90 and standard deviation of 7.036. Then we are looking for the probability. Let me remind myself of the question. We're looking for the probability that fewer than half of these bottles contain this amount. So fewer than half is less than 100, right? Probability of the number of bottles, y less than 100. And because we're using a normal approximation, we need to use a continuity correction. So this will be the probability of this distribution. And I should actually use a different variable there. I don't think it matters what variable I use. But this is a normal approximation, so let's say W is less than or equal to 99.5. So that's the continuity correction. Then we can use the normal model to find this probability. So our minimum is a large number. Our maximum is 99.5. Our mean is 90. Standard deviation 7.036. Let's plug that in and see what we get. So normal cumulative distribution, minimum, maximum, mean, and standard deviation. And I get a probability of 0.9115. 0.9115. And rounded off, this is 91.2%. Okay, so for part B, my final answer is 91.2%. Thinking about that intuitively or logically, well, I had a 0.45% chance that the amount of liquid would be between those two values. So that's less than 50% chance. And so we're looking for the probability that fewer than half of the bottles contain that amount. You're going to expect a pretty high probability because it's likely that fewer than half will have that amount, right? It's unlikely that more than half will have that amount because the probability is 45%. Okay, so the 90% or 91.2% answer makes sense there. Part C says the machine is adjusted so that standard deviation of the liquid put in the bottles is now 0.16 milliliters. Following the adjustments, Hannah believes that the mean amount of liquid put in each bottle is less than 25 milliliters. She takes a random sample of 20 bottles and finds the mean amount of liquid to be 24.94 milliliters. Test Hannah's belief at the 5% level of significance. You should state your hypothesis clearly. For this question, we're looking for a distribution of sample means. And so we're looking at the standard error of the mean for this question. Let's go ahead and set up this hypothesis test. keeping that in mind. So firstly, they give us the standard deviation of 0.16. Sorry, let's just double check the stats again. So yeah, they say the standard deviation is now 0.16 milliliters, and the sample mean that Hannah got was 24.94, and we're testing how likely is that given that the mean is 25 milliliters. Okay, so our hypothesis test is, our null hypothesis will be, well, the mean is equal to 25. Our alternate hypothesis, what we want to prove is that the mean is less than 25. And we have a sample of 20, a sample mean of 24.94, and the significance level is 5%, so alpha is 0.05. So how likely is it we would get this result given that the mean actually was 25? And our standard error of the mean, sigma x bar, is equal to the standard deviation divided by the square root of n. This is the standard error of the mean. Let's go ahead and get a number for that. This will be 0.16 divided by the square root of 20. And I get 0.035777. Rounding that off to 4 decimal places, this will be 0.0358. 0.0358, that's approximately. And then we can say this distribution of the means will be a normal distribution with a mean of 25 and a standard deviation of 0.16 squared on n, which is 20. So that is, well, that's this expression squared. So remember, you usually write the standard deviation squared to stand for the variance. Okay, so we've set the problem up. Now we're looking for the probability that d bar is less than or equal to 24.94. So we can again use the normal cumulative distribution function for this and put that into a calculator. So on our normal distribution, we've said we're assuming a mean of 25. We have a mean of 24.94. We're looking for this probability, and we're going to compare that to our significance level to see if it is significant. So this is the numbers I'm going to enter. So let's see what we get here. So entering all of that, I get a probability of 0.0468. 0.0468. And this is clearly less than alpha. So that indicates we should accept the alternate hypothesis, that the mean is less than 25. Or you could also state this as reject the null hypothesis. Again, just to be clear, I should redraw this. Just to be clear, this value here, this probability of getting this mean was about 4.69%, and we had a significance level of 5%, so it's less than that. So we accept the alternate hypothesis, and let's just finish this off. Let's say the evidence suggests the population mean is less than 25 at the 5% significance level. So there is sufficient evidence to support Hannah's belief. Okay, that was part C of question 5. So that was a 13-mark question. Onto the mechanics section now. A couple of things to point out on this front page. It says answers should be given to 3 significant figures unless otherwise stated, and also unless otherwise stated, whenever a value of g is required, take g equal to 9.8 meters per second squared and give your answer to either 2 significant figures or 3 significant figures. So I just wanted to point out those 2 pieces of information there. So on to question 1 of this mechanics section, question 6 of the exam, if you're sitting this exam. Question 1 says, in this question, position vectors are given relative to a fixed origin O. At time t seconds, where t is greater than or equal to 0, a particle P moves so that its velocity v meters per second is given by v equal to 6ti, take 5t to the power of 3 on 2 j. When t equals 0, the position vector of P is negative 20i plus 20j meters. Part A says, find the acceleration of P when t equals 4. To get the acceleration, we can differentiate the velocity. So dv on dt is equal to a. Basically, the change in velocity with respect to time is the acceleration, right? So taking the derivative of this vector here, we would have, well, using the power rule, take the coefficient of t. This will just be 6i. And then bring that power down the front, multiply it by 5. 5 times 3 on 2. That would be 15 on 2 t, and then take 1 from that power. 3 on 2 take 1 is a half. So we have, for the acceleration vector, 6i take 15 on 2 t to the power of a half j meters per second squared. And then we want the acceleration when t equals 4. So we can plug that in. A would be 6i take 15 on 2 multiplied by 4 to the power of a half, which is the same as the square root of 4, which is 2. And this is j. So then, well, those 2's would cancel. We'd end up with an acceleration of 6i take 15j meters per second squared. On to part B. Part B says, find the position vector of P when t equals 4. For the position, we can integrate the velocity. This is something you really need to understand, that the derivative of, actually write it like this, the derivative of v is acceleration and the integral of v is the position. So taking the integral of this expression now, we would have for part B, the integral of v is using the power rule, we would add 1 to that power and divide. So actually, let me just write the thing out again so you can see what I'm doing. This was 6ti. 6ti take 5t to the power of 3 on 2 j. So add 1 to the power, divide by 2. This would be 3t to the power of 2 I. Subtract, add 1 to this power, 3 on 2 plus 1 is 5 on 2. Divide by 5 on 2. 5 divided by 5 on 2 is like 5 times 2 on 5. So those 5's would cancel. So we'd have 2 times t to the power of 5 on 2 j meters. That's our position vector, plus, actually, almost forgot, plus that constant on the end. Now that constant is going to be our position when t equals 0. And they actually tell us that in the question, remember? So they tell us when t equals 0, the position of P is negative 20i plus 20j. That is giving us this constant, right? So we're saying this equals s. So let's write the full thing out. This will be 3t squared I, take 2t to the power of 5 on 2, take 20i plus 20j meters. And then when t equals 4, we will have s equal to 3 times 16. That's 48i. 4 to the power of 5 on 2. Let's just put that into a calculator. Why not? So 4 to the power of 5 on 2, something like, yeah, it's like 2 to the power of 5, kind of. That's 32. So 32j. Actually, I forgot the j there. And then we have take 20i plus 20j. So 48 take 20i, that's 28i. And then negative, oh, I just realized I forgot to multiply that by 2. So it had a coefficient of 2 there. That's going to be 32 times 2, 64. Okay, so then we have negative 64j plus 20. So that's negative 44j meters. So that is my position vector at t equal to 4 seconds. All right, so that was question 1 of this mechanics section for 6 marks. Question 2 says a particle P moves with constant acceleration 2I take 3j meters per second squared. At time t equals 0, the particle is at the point A and is moving with velocity negative I plus 4j meters per second. At time t equals t seconds, P is moving in the direction of vector 3I take 4j. Part A says find the value of t. Let's firstly summarize the information. So they tell us that we have an acceleration of 2I take 3j, and at time equal to 0, or the starting time, we have a velocity of negative I plus 4j meters per second. And then at time t seconds, the particle is moving in the direction of vector 3I take 4j. Now remember that velocity indicates direction. So when you talk about a velocity vector, that also is telling you what direction the particle is moving. So if we're told the direction, we know that the velocity is some multiple of that vector. So we can say the velocity here is going to be some multiple of the direction of movement. So it'll be k times 3 take 4j. You could also state from this piece of information that the ratio of the I and j vectors is in the ratio 3 to negative 4. So that's another way of thinking about that. So now we're going to use the fact that velocity equals the initial speed plus the acceleration times time to create an equation which we can solve for t. So we have the initial velocity, it's negative I plus 4j. We have the acceleration, it is 2I take 3j times t. Now if we rearrange this, we're going to have a general velocity vector for any time t. So expanding those brackets, we'd have negative I plus 4j plus 2ti take 3tj. And then rearranging in terms of I and j, we would have 2t take 1i, and then 4 take 3tj. So basically just combining like terms there. So this is my general velocity vector for any time. Comparing it to this one here, I know that the coefficients of I and j need to be in the ratio 3 to negative 4. Another way of stating this is if you rearrange this, or I could write it like this, I on j equals 3 on negative 4, and then negative 4i equals 3j. So they're the coefficients, so I need the negative 4 times the coefficient of I. So negative 4 times 2t take 1, and that's going to equal 3 times the coefficient of j. So 3 times 4 take 3t. And now I have an equation that I can solve for t, and I should be using a large T here because this only holds at time equal to t, large T, capital T seconds. Okay, so then solving this for capital T, expanding out, I have negative 8t take, or plus 4, equal to 12 take 9t. Combining like terms, negative 8 plus 9 is t. 12 take 4 is 8. So I have t equal to 8 seconds there for my final answer for part A. Part B says at time t equal to 4 seconds, P is at the point B, find the distance AB. For this I'm going to use the formula to find position. So down onto the next page for part B, one of the position formula says that the position equals the initial speed times time plus half the acceleration times the time squared, and this should be enough to get our answer here. So our initial speed, or our initial velocity vector, was negative I plus 4j times the time, and we also have an acceleration vector that was 2I take 3j times time squared, and we are looking for the position when t equals 4 seconds, so plugging that in, when t equals to 4, we would have s equal to negative, well, let's just write it out and then expand, so this will be multiplied by 4 plus a half, all of this multiplied by 4 squared, which is 16, and then we would have negative 4i plus 16j. 16 divided by 2 is 8 times 2 is 16 again, 16i, and then 8 times 3 is negative 24j. Simplifying this, I'll have negative 4i plus 16, that is 12i, 16 take 24, that is negative 8j meters. So that's my position vector, and we're looking for the distance AB. That's going to be the modulus or the magnitude of this vector, right? So basically we started at A, we traveled to B, however that looks, and we're looking for the size of that vector. We can take the modulus, which is, just using Pythagoras. So taking the modulus of the position vector, we take the square root of 12 squared plus 8 squared. This is the square root of 144 plus 64. What would that be? 144 plus 64. We might be able to simplify this. So 208. Well, let's just take the square root. Why not? So 14.42 and so on, rounding off. So we're meant to round off to 3 significant figures. So 14.4 should be fine there. So this is approximately 14.4 meters for the distance AB. I'm sure a simplified surd is fine for a final answer there as well. It doesn't specify in the question. So that was question 2 of the mechanics section for a total of 8 marks. Again, final answers were 8 seconds and 14.4 meters. Question 3 gives us a figure, and when you see this figure, I'm sure your heart jumps with joy. You know how great these types of questions are with pulleys and boxes and things. But anyways, this question says 2 blocks A and B of masses 2m and 3m respectively are attached to the ends of a light string. Initially, A is held at rest on a fixed rough plane. The plane is inclined at an angle of alpha to the horizontal ground where tan of alpha equals 5/12. The string passes over a small smooth pulley, P, fixed at the top of the plane. The part of the string from A to P is parallel to a line of greatest slope of the plane. Block B hangs freely below P as shown in figure 1. The coefficient of friction between A and the plane is 2:3. The blocks are released from rest with the string taut and A moves up the plane. The tension in the string immediately after the blocks are released is T. The blocks are modeled as particles and the string is modeled as being inextensible. Part A says show that T equals 12 mg over 5. Okay, so a couple of things to note. So we're assuming this plane is a rough plane and we have a coefficient of friction. So we do have to consider friction here. And also the pulley is smooth, so there is no friction around the pulley. The string is inextensible, so the tension force is going to be the same at where it's pulling on A and also where it's pulling on B. So that's nice. We can assume that is the same at both points. And really the key to these pulley type questions with masses on either side is that when you release them, they're going to be moving at the same rate, right? Their acceleration is going to be the same. And usually either the masses are the same or we have some ratio of the masses. In this case, the ratio is 2:3. So we can say that the ratio of the forces, because the accelerations are the same, the ratio of the forces will be 2:3 as well. And we can go ahead and find the net force on each one. For B, it's going to be, we're going to look at it vertically. For A, we're going to look at it horizontally. And essentially it becomes a simultaneous equations question. So let's go ahead and get started on that then. For part A, I might start this on the next page. We're going to need plenty of room here. For A, we're not assuming, we know that the accelerations, once they're released, the accelerations are equal for each box. And also I'm going to be using the fact that F equals MA as well. Okay, so let's firstly consider block A and the forces acting on block A. And as I said, we're going to look at the forces acting horizontally parallel to the plane. So firstly, I've already drawn one in. We have the tension force here pulling the box, the mass up the plane. We're going to have the weight pulling down on the mass, and we're going to have some parallel component of that pulling down the plane. Sorry, these vectors are not the right size, but I'm just using them to indicate direction. So this is going to be mg, or I should write 2mg because we know the mass is 2m, so 2mg, and this component is going to be 2mg sine alpha. And also we know there is a perpendicular component of this weight, that's 2mg cosine alpha, and the normal force reacting to that pushing back on the box perpendicular to the surface, that's going to be equivalent or have an equivalent magnitude as 2mg cosine alpha. That's important because we need to think about friction. Friction is a multiple of the normal force. So friction, because we are told the mass A is moving up the plane, friction is in the opposite direction of movement. So this will be our coefficient of friction, which we know is 2 on 3. Remember, they tell us that in the question. The coefficient of friction is 2 on 3. So this is going to be 2 on 3 times 2mg cosine alpha. I'm just going to write n there because I don't have enough room. So we have the forces acting horizontally. T is pulling up the plane. We have the weight pulling down, a component of the weight pulling down, and we have the friction acting against movement as well. That will give us a net force acting in the direction of movement. And we know that force equals ma, so we'll have some net force we can plug into this equation. So again, thinking or resolving horizontally, we've got T pulling up the plane in the positive or the direction of movement. We're taking away that parallel component of weight force 2mg sine alpha, and also the friction force, which is 2/3 2mg cosine alpha. This is equal to the force, the net force. Now this is the mass times acceleration. In this case our mass is 2m, and we're just going to call acceleration a because we don't actually know what that is. Let's just use a. Also now I think it's a good time to note that tan of alpha equals 5/2. They tell us that in the question, and therefore we can find sine of alpha and cosine of alpha. So just to illustrate this, if we drew a right angle triangle with alpha, this is meant to be a right angle triangle, tan, the ratio tan is opposite over adjacent, so this will be 5/12, and then you can find the hypotenuse. So 25 plus 1, well, let's just do that on a calculator. So we've got the square root of 144 plus 25, and we get 13. So the hypotenuse is 13. Therefore, we can find sine of alpha. I probably should do this more properly, but sine of alpha is opposite over hypotenuse. That's going to be 5/13. And the cosine we can also find, that's going to be adjacent over hypotenuse. That's 12/13. So plugging those values into this equation now, we'll have T take 2mg times 5/13. Sine of alpha equals 5/13. Subtract, simplifying this fraction here, 2/3 times 2 is 4/3. mg times cosine of alpha is 12/13. This equals 2ma. Let's try to simplify this now. This would be 2 times 5 is 10 mg/13. This is, simplifying this, I would actually cancel. So 12 divided by 3 is 4. And then I have 4 times 4, which is 16 mg/13, because that 3 cancelled out. This is equal to 2ma. And then I have negative 10 take 16. That's negative 26 mg/13. This would simplify to negative 2. So over here, all of this simplifies down to negative 2 mg, and this is all equal to 2ma. Okay, so I have a fairly simplified equation from considering block A. Let's move on to block B now. Let's say consider block B. Block B, and we are thinking about the forces on this acting vertically in the direction of movement. Let's have a look at the diagram again. We have the tension force pulling up on block B, we have the weight pulling down. This is just going to be 3 mg, because they tell us the mass is 3m. So 3 mg pulling down in the direction of movement for B, and this is going to give us some net force acting in the direction of movement. So we have the weight pulling down positive, because that's the way the block is moving. Subtract the tension force in the string pulling up. This is equal to the net force, mass times acceleration. So the mass is 3m times the acceleration. The acceleration here is the same as block A, so we can use the same variable we used for the first equation here, so just A as well. And that's really the key that allows you to rearrange and solve for T. So I'm going to rearrange this in terms of MA. So divide by 3, I'd have MA equal to 3 mg, take T on 3. If I rearrange this equation up here in terms of MA, I would have MA equal to T take 2 mg on 2. So now I can set those two things equal to each other and solve for T. So therefore, I have T take 2 mg, actually multiplied by a half, might be a slightly easier way to write it. This is equal to 1/3 times 3 mg take T, and then multiplying through by 2 and 3, I'd end up with 3T take 6 mg equal to 6 mg take 2T. Keep simplifying. Actually 3T plus 2T, that would be 5T equal to 6 mg plus 6 mg, that's 12 mg, and then T is equal to 12 mg on 5. And that is what I believe they wanted us to end up with. Show that T is equal to 12 mg on 5, and I guess that's in newtons because we're talking about the tension force. Okay, that was part A, for 8 marks. I actually want to point out where the marks are. The marks are largely in here for actually finding the correct equations for resolving the forces for each mass. There are, I believe, 6 marks in there just for those equations there, and I think there's a couple marks for the final answer. So check out the mark scheme if you want to look at that in detail. On to part B. After B reaches the ground, A continues to move up the plane until it comes to rest before reaching P. Part B says determine whether A will remain at rest, carefully justifying your answer. Before it reaches P, it comes to rest at some point up here, and we want to know, will it move down the plane or will it continue moving up? So what are the forces acting on this block when it comes to rest? Well, we'd have the weight still pulling down, and this time we'd now have the friction pulling up, okay, because we only have a force pulling the particle down. So you could think of it initially as it would very briefly start to try to move down the plane, and then friction would start moving the opposite direction. So we need to compare these two forces. Whichever one is larger will determine if the particle or the box stays at rest or starts to move back down the plane. So comparing those two forces for part B, I might just draw a quick diagram for illustrative purposes. You wouldn't have to do this in the exam. So we've got forces acting on A, we have the box here, and we've got essentially gravity pulling down, and we've got the horizontal component of that, or the parallel component of that, 2 mg sine alpha, and then we have friction pulling up the plane, which is 2/3 2 mg cosine alpha. Comparing these two forces, we actually found those before in part A. Remember, we found values for these. We got 10 mg on 13 and 16 mg on 13 for those two parts. So just pulling that straight from part A, I'm going to write this as 10 on 13 mg, and this was 16 mg on 13. Obviously, the frictional force is larger, so we can say the frictional force is greater than gravitational force. and therefore the block would stay at rest. So therefore block A would stay at rest. Okay, that was part B. Part C says suggest 2 refinements to the model that would make it more realistic. All right, what have we not considered? We have not considered friction around the pulley. They have not told us the sizes of the blocks, so therefore we're not considering air resistance. The weight of the string, we haven't considered that. There's quite a few things you could include in here to make it more realistic. So for part C, because it was 2 marks, let's write 2 things. Let's say friction of the pulley, and let's say the weight of the string. Okay, so that was question 3 of this mechanics part, question 8 on the exam, for a total of 12 marks. Question 4 gives us a figure, and it says a ramp AB of length 8 meters and mass 20 kilograms rests in equilibrium with the end A on rough horizontal ground. The ramp rests on a smooth, solid, cylindrical drum which is partly under the ground. The drum is fixed with its axis at the same horizontal level as A. The point of contact between the ramp and the drum is C, where AC equals 5 meters, as shown in figure 2. The ramp is resting in a vertical plane which is perpendicular to the axis of the drum at an angle theta to the horizontal, where tan theta equals 7/24. The ramp is modeled as a uniform rod. Part A says explain why the reaction from the drum on the ramp at point C acts in a direction which is perpendicular to the ramp. Alright, so they tell us that it is a smooth, solid, cylindrical drum. Smooth meaning we're not considering friction between the rod and the drum. If there's no friction, then there's no other forces other than the force pushing from the drum on the rod, which will be perpendicular to the ramp. So basically the idea is there is no friction between them. Okay, so that's my answer for part A. There is no friction between the ramp and the drum. Another way of saying that, I guess, is the drum is modeled as smooth. The drum is modeled as smooth. Okay, so therefore force is entirely perpendicular. Okay, sorry for the messy writing. That was part A. Part B says find the magnitude of the resultant force acting on the ramp at A. So at A, we're going to have some vertical component of force and some horizontal component of force. We're looking for the resultant, or the net, in effect. To find the resultant force, we need the net vertical force acting at A and the net horizontal force acting at A. How do we find those? Well, we need to consider all of the other forces acting on the rod, and then hopefully solve for these 2 forces here. So I don't know where I rubbed those out, by the way. So this force here, the vertical force pushing up on the rod at A, we can say is the reaction force. So this is the force pushing up on the rod at A from the ground. This force here in the horizontal direction is going to be the frictional force. And because we're going to be taking moments on particular points on this rod, we want the perpendicular aspects of those 2 forces. So this will be r cosine of theta, and the frictional force, that would be f sine theta. If you're not sure if it's cosine theta or sine theta, try to picture where theta would be in that little triangle. Theta's here and theta's here. Okay, so we have those 2 factors. Now, other forces to consider in this diagram is the force, the normal force pushing from the rod from the drum. Let's call that N. We have the mass of the rod, that would be halfway, because it's a uniform rod. We would have mg pulling down and the components of that. So this will be, in this case, actually, they tell us the mass is 20 kilograms. So we could say this will be 20g. So then the parallel component of that is 20g sine theta, and the perpendicular component is 20g cosine theta. And they're all the forces we're going to need to consider. A couple questions you might have: why is friction pulling this way? Well, think about what this rod would do. It would be pushing this way, right? Because that mass wants to fall to the ground. So that would be pushing this way. Also, it doesn't really matter. You can assume it's this way or the other way. You'll still end up with the correct answer. Also, why haven't we called this the normal force, r cosine theta? You could introduce another variable. You could call this one normal force 2 and this one normal force 1, but that introduces extra variables. So rather call this a component of the reaction force, and then you have less variables to solve for. Okay, so let's go ahead and get started on this question and see if we can't make some sense about it. So for part B, we are looking for the resultant force at A. All right, we can start off by taking some moments. So moments around A is where I'm going to start. You can take moments, or it makes sense to take moments around C and B as well. I'm starting at A because it effectively cancels out all of these forces around here. So I'm just having to consider the weight and the normal force at C. So taking moments around A, the only force going anti-clockwise is the normal force at C, and the only force going clockwise is the perpendicular component of weight, so 20g cosine theta. We need to set them equal to 0 if we multiply them by the distance from A. The total length of the rod is 8 meters, therefore the distance from the center of mass is 4 meters. So multiplying this by 4, this is going to be 5 times n. So we can say that 5n is equal to 20g cosine theta times 4 is distance from A. This actually allows me to solve for n because I can find the value for cosine theta as well. So simplifying first, I'd have n equal to 80 divided by 5. That would be 16g cosine theta. And remember, in the question, they tell us tan theta equals 7 on 24. So let's make a note down here. Tan theta equals 7 on 24. So you can always draw a right angle triangle to help this make sense. But the tan ratio is the opposite over the adjacent side. To find the hypotenuse there, we can use Pythagoras' theorem. Let's do the square root of 24 squared plus 7 squared. That gives me 25. So the hypotenuse there is 25. Therefore, the cosine of theta is adjacent over hypotenuse, 24 on 25. Plugging that in here, we would have 16g times 24 on 25. Let's get a number for that. So we've got 16 times 9.8. Remember, we need to assume g is 9.8. Multiply that by 24 on 25. And I get 150.528. 150.528. Okay. I have n. Now I want to take moments around another point. I could do B or C. I might do C because then I don't have to consider n as well. So if I take moments around C, I have the perpendicular component of the reaction force at A, the perpendicular component of the frictional force, and also 20g cosine theta. So this force here needs to equal these two forces, again, because it's in equilibrium. So for moments around C, we have the weight, 20g cosine theta multiplied by 1 is 1 meter from C. I'll just point out I didn't make that point. So AC is 5 meters. This is at 4 meters. So that distance there is going to be 1. So we just multiply that by 1. So it's just going to be 20g cosine theta plus the frictional force multiplied by its distance, 5 times F sine theta equals 5, multiplying that by its distance, 5r cosine theta. Okay, we can simplify this, but you might notice we have two variables, so we're not actually going to be able to solve this for F or R, but let's simplify a little bit. We can divide through by 5, we would get 4g cosine theta plus F sine theta equal to r cosine theta. And I'm just going to leave that there for a moment. Now, if you take any more moments, if you take moments around B or even moments around the center of mass, it's not going to help you because you're still going to have these two variables. So what we need to do now is to solve for one of those by resolving either vertically or horizontally. I'm going to consider the vertical forces. So the vertical forces in total are R. We also have a vertical component of N. This would be N cosine theta. And we have the weight pulling down. Again, because in equilibrium, all of those, or those two forces added, need to equal 20g. So that is going to be an equation that allows me to solve for R. So let's say resolve vertically. We can say R plus N cosine theta is equal to 20g. I have a value for N, remember, and I can work out 20g. So R is going to be 20g take N cosine theta, plugging that all into a calculator. I have my value of N here still on my calculator. Cosine of theta is 24 and 25, so this will be 20 times 9.8. Subtract that answer I had multiplied by 24 on 25. Okay, I get there a force or a value for R of 51.49. 51.49 rounded off. So that's approximately. Okay, and that's in newtons. And now then I can plug that in here and solve for F. So F would equal, rearranging this, I've got R cosine theta take 4g cosine theta all over sine theta. Plugging in all of those values, also I can find sine theta as well. R was 51.49 multiplied by 24 on 25. Take 4 times 9.8 times 24 on 25. 25 divided by sine theta. Going up here now, sine theta is opposite over hypotenuse, 7 on 25. So this is going to be 7 on 25 there in the denominator. Okay, let's plug that, all of that into a calculator and see what we get. So taking that previous answer, multiplying that by 24 on 25. For the numerator, I get 11.8 approximately. Then I'm going to divide that by 7 on 25. And I get 42.14. Or 42.15 rounded off, 42.15. Okay, so remember what F and R were. They were the vertical and horizontal forces acting at A. So the resultant force then is going to be the vector we get, or the magnitude of the vector we get when we add these together. So if I add those, I can find the resultant force. So let's go ahead and do that. Essentially, we're using Pythagoras to get the magnitude. So magnitude of the resultant force is going to be the square root of r squared plus f squared. So plugging that in, actually, let's just put that straight into a calculator. I've got f here, so the square root of that answer squared plus f. Sorry, R was 51.49 squared, and I get a resultant force of 66.54. Rounded off, this would be 66.5. 66.5 newtons. Alright, so that is my final answer there. Hopefully that is making some sort of sense. Just checking, find the magnitude of the resultant force acting on the ramp at A. There we go. They haven't asked us to find the direction either, so we don't have to consider direction. Part C says the ramp is still in equilibrium in the position shown in figure 2, but the ramp is not now modeled as being uniform. Given that the center of mass of the ramp is assumed to be closer to A than to B, state how this would affect the magnitude of the normal reaction force between the ramp and the drum at C. Alright, so the center of mass is now closer to A. I'm going to rub all of this out just so we can have a look at this. The center of mass is assumed to be closer to A over here somewhere. And what effect would that have on the force at C, the normal reaction force? Well, consider a lever, right? What's the point of a lever? The point is, the longer the lever, the less force you have to put on it to lift something heavy. Let's say you have a heavy object. If you have a really long lever, you don't need much force to lift up that object. So the point is, the further away the force is from the center of mass, the less force you need to achieve the same effect. So if you have a short lever, I'm sure you've tried this in the backyard, lifting things up, or even on a seesaw or something like that. The shorter the lever, the harder it is to lift that mass. So the same principle is going on here. We've moved the center of mass away from C, therefore the forces at C will decrease to keep the rod in equilibrium. So therefore my answer there is the magnitude decreases, or the magnitude of the normal reaction force decreases. So let's go ahead and summarize that for part C. So the center of mass moves away from C, therefore the normal reaction force decreases. Okay, so that was 1 mark for part C and a total of 11 marks for question 4 of this mechanics section. Question 5 says the points A and B lie 50 meters apart on horizontal ground. At time t equals 0, two small balls P and Q are projected in the vertical plane containing AB. Ball P is projected from A with speed 20 meters per second at 30 degrees to AB. Ball Q is projected from B with speed U meters per second at angle theta to BA as shown in figure 3. At time t equal 2 seconds, P and Q collide. Until they collide, the balls are modeled as particles moving freely under gravity. Part A says find the velocity of P at the instant before it collides with Q. For these types of questions, you want to think of the velocity in terms of its vertical component and its horizontal component. So the horizontal component of velocity is not affected by any forces because we're not considering air resistance. Because it says, remember, moves freely under gravity. That's meaning there is no air resistance to consider. So the vertical component is always the same in these situations. The horizontal component is always the same. The vertical component is affected by gravity. And because they tell us how long it takes for them to collide, we can figure out how much that vertical component changes because the force or the acceleration due to gravity is always constant. So let's go ahead and have a go at answering this using that approach. So firstly, let's find the horizontal component of the velocity. Now they give us this angle here of 30 degrees. So this part of this, or this horizontal vector, is going to be, actually it might be easier if I draw them on the other side. So this will be the adjacent side to the angle. This is the hypotenuse of 20. So this vector here is then going to be cosine 30 times 20. So cosine of 30 times 20. Let's find that. So cosine of 30, actually I've got to make sure it's in degrees because they gave us the angles in degrees. So change your calculator into degrees if you need to. Cosine of 30 multiplied by 20, that gives me approximately 17.32 for horizontal velocity. 17.32 meters per second. And then I want to think about the vertical aspect of this. I can do sine of 30. You might even actually know what sine of 30 is already, so you know the answer, but let's do sine of 30 times 20. I get 10 because sine of 30 is a half. Okay, so they're the initial velocities. This one's not going to change, remember, but at t equals 2, we can also work out the vertical velocity. So we can say this is going to be, let's say the final velocity is the initial velocity, take a times t, so 9.8 times 2, 10 times, or take 9.8 times 2, let's just put that into a calculator, take 9.8 times 2. I get negative 9.6. So negative 9.6 for the velocity after 2 seconds, the vertical velocity. And then we're looking for the velocity of p, so we need to find the resultant of those two. So let's say velocity of p is equal to the square root of these using Pythagoras. 17.32 squared plus 9.6 squared. Putting that into a calculator, we get 19.8 approximately, 19.8, so round it off. And because it's a velocity, we also need a direction. Always be careful with these questions, whether it says speed or velocity. We need a direction, and well, this is a negative velocity, so it's obviously falling back towards the ground. And we have this horizontal velocity here, 17.32 and negative 9.6. We can use the tangent ratio to find that angle. So we're going to have the inverse tan. So let's say theta equals inverse tan of opposite over adjacent. Putting that into a calculator, we have got 9.6 divided by 17.32. I get 28.998. So I'd round that off to 29 degrees. 29 degrees. Sorry. 29 degrees below the horizontal, so towards the ground. So at 29 degrees below horizontal. Okay, there we go. That is my final answer for part A. Part B says find the size of angle theta and the value of u. So I shouldn't have called that theta, sorry if that's confusing, but this theta is talking about this one here, this angle that ball Q is projected at. So we're looking for u, the initial velocity of Q, and the angle that it was projected at, and we know that they collide at 2 seconds. We also know that ball P is on its way down when they hit. Okay, so they hit somewhere in that arc when P is on the way down towards the ground. We can find how far P has traveled in terms of its horizontal distance because we have its horizontal velocity or speed and we have the time it was traveling, so we can find that distance. Therefore, we can also find the horizontal distance Q has traveled and therefore find its horizontal speed. And then I'll point out why we know that Q is also on its way down when they collide as well. Okay, so let's firstly find their horizontal distances. So we're going to have the speed. So for part B, we have the speed, the horizontal speed of ball P. That was 17.32 times the time. 17.32 times the time. This is, actually I don't need a calculator for that. I'm getting lazy. This is going to be 34.64 meters. And because we know they were fired 50 meters apart, we can work out this is going to be 50 take 34.64. So 50 take 34.64, that's going to be 15.36 meters. So this is the distance, horizontal distance covered of ball Q, and so its horizontal speed is going to be the distance it's traveled divided by the time, 2. So 15.36 divided by 2, 15.36 divided by 2, that's going to be 7.68 meters per second. Now for the vertical vector of the velocity for Q, how do we know this is not all still on the way up when it hits P? I don't know, maybe this is obvious to you, but I had to think about it a little bit. If it was still on the way up, that means it's going to go higher than point P or ball P. Therefore, it must be traveling faster in the vertical direction than P. But if it's traveling faster, then it would be higher than P at that after 2 seconds, and it should have traveled further vertically. So if P is already on the way down, Q must also be on the way down. But that's a contradiction, right? It can't be both traveling faster but also slower, because if it's on the way up when P is already on the way down, it must be going slower then, right? So they must both be on their way down towards the ground when they collide, and they must have the same vertical component of their velocity because they've traveled the same vertical distance. They've both gone up to the same height and down again and hit at the same place. So we can say then the velocity, the vertical vector of the velocity for Q will be equal to P. So they both have a vertical velocity of 10 meters per second. Okay, so we have essentially U now, and we can find the direction. So for part 1, we were looking for theta. So it's fired at some angle theta. We have this component, this vector, this was 10. We have this vector, this was 7.68. So to find theta, we can use the inverse tan of 10 on 7.68. So theta equals inverse tan or arctan of 10 on 7.68. Putting that into a calculator, 10 on 7.68, I get 52.47, rounded off to 52.48. So rounded off 52, not 42, 52.48 degrees. And then for part 2, they wanted the U, that was this part here. So using Pythagoras, we can say this is going to be 10 squared plus 7.68 squared. Putting that into a calculator, 10 squared plus 7.68 squared, I get 12.6, approximately 12.6 meters per second. Okay, that was part B, part 1 and 2. Part C says state one limitation of the model other than air resistance that could affect the accuracy of your answers. Let's have a careful look at the question. It says they are modeled as particles moving freely under gravity. So when they're modeled as particles, it means we don't have to consider the size of the ball and therefore how that size would affect their flight through the air. So I'm going to say the size of the particles or the size of the balls is something we could consider. So the size of the balls. Other things you consider there are if they're spinning when they're projected, or are they just flying through the air without any movement at all. Wind as well, and the exact value of gravity. So we're assuming gravity to be 9.8 meters per second squared, but you could take a more accurate value of G as well. Okay, and that is the final question in this exam. That was question 5 of the mechanics section for a total of 13 marks. I hope you got some value out of this video. As always, feel free to leave a comment on any of the questions or any questions you might have that I didn't go into enough detail on, etc. Please feel free to leave a comment. And if you find these useful, let me know by leaving a like. That's really the best indicator that I have that people show me that they enjoy the videos and they want me to keep making them. So please leave a like if you do want me to keep making these videos. Subscribe if you want to see the other videos I'm making, and I'll see you in the next one. Bye for now.